You've probably made one of these before, right? A simple little origami paper cup. It seems like just a fun, quick craft project. But today, we're going to unfold the pretty surprising mathematical secrets that are hidden right inside. It's going to be a journey into geometry, into data, and, well, into the funny ways our own brains can trick us. Okay, so just take a look at this cup. I mean, it's just a folded piece of paper, right? Something you could probably whip up in a minute or two. But what if I told you this simple little thing is actually a gateway, a way to understand some really beautiful, elegant math, and maybe more importantly, to see just how easily our own intuition can lead us astray. All right, let's just jump right in with a question for you. If I were to fill this cup, let's say it's made from a standard 6-inch square of paper, if I filled it to the brim with pinto beans, how many do you think it could hold? Seriously, make a guess right now. Just go with your gut feeling. You got a number in your head? Okay, hold on to it. We're going to come back to that. So here's what we're going to do. We'll start with this deceptive little cup, then fold our way into the math. We'll see how our intuition stacks up against actual data, then explore what happens when we scale things up. And finally, we'll uncover all the cool math that's hiding in plain sight. Okay, so first things first. Before we can really solve the puzzle of this cup, we kind of have to build it, right? And you'll see that the way it's made, that's our very first clue to all the math that's packed inside. And you know, the steps are actually super simple. You just start with a square piece of paper, you fold it into a triangle, then you make a couple of these really clever folds on the corners, tuck in the top flaps, and pop it open. That's it. Anyone can do this, which is exactly what makes it such an amazing little tool for exploring some big ideas. See, with every single fold, you're not just creasing paper, you're actually physically engaging with geometry. That flat 2D square starts to transform. It goes through a series of triangles, a pentagon, even a trapezoid, until it becomes a 3D object. It's math that you can literally feel in your hands. How cool is that? All right, now for the really fun part. You remember that number I asked you to guess a minute ago? Well, it's time for the big reveal. Let's see how our intuition, our gut feeling, stacks up against cold, hard reality. So check this out. In a classroom experiment, students were asked to do the exact same thing you just did. Just look at the cup and guess how many beans it could hold. The whole point of this first step is to capture that initial guess, right? That intuitive feeling we have about three-dimensional space. And here are the results. Wow. Okay, so on the left, that first box plot shows you the range of all the guesses people made. And on the right, that's the actual number of beans the cups held. I mean, look at the gap between those two. It's not just noticeable, it is huge. So let's put a number on it. Based on the data from a 2018 study, the average number of beans people thought the cup could hold was 63. So how'd you do? Was your guess anywhere close to that? But the actual average number of beans the cup really held was 160. That's more than double the average guess. In fact, get this, in the experiments, even the highest, most generous guesses were still often lower than the smallest actual measurement. Wild, right? And hey, this isn't about being bad at guessing. Not at all. It's just a really powerful demonstration of how, well, unreliable our intuition about volume can be. We just tend to underestimate the capacity of 3D objects. And that's exactly why we need things like data and mathematical reasoning to kind of keep our gut feelings in check. Okay, so that was fascinating. But now for a classic what-if question. We've seen how our intuition can kind of fail us on a small scale, but what happens when we start to go bigger, when we change the dimensions? All right, so think about this. Our first cup was made from a 6-inch square of paper. What do you think happens if we make one from a 12-inch square? So we've doubled the side length. Does the volume double? Triple? What's your gut tell you this time? You know, a really common guess is that it would hold 4 times more. And that makes sense. There's a story of one student who even proved it by flattening the small cups and showing that, yep, 4 of them fit perfectly onto the flattened large one. That's perfectly logical thinking, if you're thinking in 2D. But a cup isn't flat, is it? It's a 3D object. And in the world of 3D, when you double the side length, you actually get 8 times the volume. 8. This gets at a really core concept called dimensional reasoning. See, when you scale up a 2-dimensional shape, like a square, its area increases by the square of how much you scaled it. Double the side, 4 times the area. But when you scale a 3-dimensional object, its volume increases by the cube of that factor. Double the side, 8 times the volume. It's a super common misconception, but it's one that math explains perfectly. And what's so powerful about this is that we can turn it into a rule. We can generalize it. Using the data we got from our little 6-inch cup, we can actually create a formula to predict the volume for a cup made from a square of any side length. We just call that side length n. You take your new side length n, divide it by 6 to get the scaling factor, you cube that number, and then multiply it by our original 160 beans. Boom, you've got a really solid prediction. This is where math becomes like a superpower. It gives us predictive power. Okay, so we've seen the math and the data, we've seen it in the volume and scaling, but what about the folds themselves? What if we unfold the cup and look at the geometric map left behind in the creases? Trust me, there are still more secrets to uncover here. What looks like just a few random folds, when you lay it flat, you can see it's actually creating this beautiful map of precise geometric relationships. This diagram really reveals that the way you build the cup, it's not random at all. The whole thing depends on some very specific, very elegant rules. Remember that one specific fold, the one where you have to line up an edge to make a parallel line? Well, it turns out that one simple move is also cutting an angle perfectly in half. It's creating what's called an angle bisector. And that single move is what guarantees that this shape here, AGFE, is a perfect rhombus, a diamond with 4 equal sides. It's just amazing. All these elegant geometric principles are all working together, completely hidden in plain sight. And we can actually take it even one step further. Using all those geometric properties we just found, we can bring in a little algebra and figure out a precise formula for the surface area of the finished cup. All you need to know is the side length, S, of the original square piece of paper you started with, and you can calculate it. Exactly. And that right there is the incredible journey of the simple paper cup. We started with a hands-on craft, right? Then we challenged our own intuition with some real data. We explored the totally surprising effects of scaling it up. And finally, we uncovered this beautiful, elegant geometry and algebra that, well, it was there the whole time. So what's the big takeaway here? What does all this mean? It means that math isn't just about numbers and formulas in a dusty old textbook. It's a powerful lens for curiosity. It gives us a framework to question our own intuition, to test our assumptions, and to discover the surprisingly complex and beautiful systems that are running the show behind even the simplest objects around us, like this paper cup. Which really just leaves us with one final thought. All of this was just from a simple paper cup. So now I want you to take a look around you, right now. What mathematical secrets do you think are hiding in the objects on your desk, or in your kitchen, or maybe right outside your window?